So some early misconceptions about the ocean floor. So until the mid 1900s, most people believed the ocean floor was essentially flat. That it was just sort of this flat, muddy abyss, pretty much. They also believed that the oceanic crust was much older than the continental crust. The whole idea being that the ocean was there and somehow the continent sort of rose out of the ocean, possibly by volcanic activity or something like that. But that was the original idea, was the oceans were first and then everything else kind of built up out of the ocean somehow. New technology, though, in the 1940s, 1950s showed that both of these ideas were wrong. So mapping the ocean floor. So a magnetometer is a device that can detect small changes in magnetic fields. It's basically kind of what we're using with our magnetic field sensors that we're going to play around with later. But it's basically a sensor that detects small changes in magnetic fields. That's what a magnetometer is. But you tow this behind a ship, and it can basically record the magnetic fields generated by ocean floor rocks. And the rocks basically have iron in them. The iron makes little permanent magnets when it crystallizes. So there is a magnetic field generated by these rocks. Sonar uses sound waves to measure distances. We've talked about that before. Uses the time that it takes for sound waves sent from the ship to bounce off the ocean floor and return. Then it calculates the depth of the ocean. This enabled scientists to measure water depth and map the topography of the ocean floor. There's some areas we have fairly detailed maps. Other areas it's less detailed. We get a good idea of what's down there. All right, ocean floor topography. So scientists were surprised to discover vast underwater mountain chains. We call those the ocean ridges or the mid-ocean ridges, really. I need to fix that typo, I think. But these run around the globe like the seams on a baseball, and that's an analogy you'll hear. We've already heard it once, I think, in a documentary. We'll hear it in at least one more. These form the longest continuous mountain range on Earth. It's up to 65,000 kilometers long, up to 3 kilometers above the ocean floor in places. Sort of the average is about 2.5 kilometers. So, earthquakes and volcanism are common along the ridge because it's basically a divergent plate boundary. You got two tectonic plates that are moving away from each other. You got new seafloor being formed there. That's broken into something called the fracture zone, where you got smaller plates that are kind of sliding past each other. So there's a lot of earthquakes there. And then trenches are deep valleys in the ocean floor. They also found those. Some of these are thousands of kilometers long, several kilometers deep. And again, the deepest is the Mariana Trench and the Pacific Ocean at 11 kilometers deep. I feel like we keep coming back to the Mariana Trench, but it's the most famous one, so why not? So this is a map of where some of the ocean ridges and deep sea trenches are. If we kind of look here, we have the two main ones we kind of talk about and hear about in documentaries and such are the East Pacific Rise, which is basically running right here through the Eastern Pacific Ocean. And then the Mid-Atlantic Ridge, which runs right down the middle of the Atlantic Ocean here. But you got some others. You got the Chile Ridge, you got the Pacific Antarctic Ridge, etc. But the two most common ones we'll hear about are the East Pacific Rise and the Mid-Atlantic Ridge. Also, the Mariana Trench is located over here in the Western Pacific. And it's kind of south of Japan, kind of north of Australia and New Zealand. So it's kind of like right up here. It's the only trench that's really mentioned on here, but if we could label really the Chilean Trench, which is kind of like right off the coast of South America here. So ocean rocks. So in addition to making maps, sediment and rock samples were collected. So we have maps of the ocean floor. We also started collecting sediment samples and rock samples to look at. For the rock samples, the ages of rocks vary on a predictable pattern across the ocean floor. The rock samples taken near the ridge are younger than those taken near the trenches. So if you have your ridge and it kind of goes across and you got a trench here, they are younger near the ridge. Okay. They get older as you get closer to the trench. All right. So the rocks get progressively older as you move away from the ridges. It's also symmetrical on either side of the ridge. So in other words, if I have a band like right here that is, say, 100 million years old, then if I went about the same distance on the other side, I'd also have another band that's 100 million years old. Whole idea being symmetry means if you divided it right down the ridge, you're going to have the same ages of rocks on both sides in the same pattern. Even the oldest rock samples from the seafloor are geologically young at 180 million years old. So the oldest rocks on the seafloor are not that old compared to the continental crust. So those are actually much younger than continental rocks, some of which are about 4 billion years old. So some of our continental rocks on the order of 4 billion years old. Some of the oldest rocks on the seafloor, 180 million years old. So that's a huge difference there. So ocean sediments. So ocean floor sediments are typically a few hundred meters thick. Large areas of continents have sedimentary rocks that can be up to 20 kilometers thick. So in other words, sediments on land can be a whole lot thicker than they are on the ocean floor. The difference in sediment thickness was puzzling, but the leading hypothesis was that the ocean sediments were thinner because the oceanic crust was younger. If it's younger, it has less time for sediments to build up. So therefore, you'd have thinner sediments. If it's older, you'd have more time for sediments to settle there. Think about like something you've put on a shelf. When you first put it on the shelf, no dust on it, right? If you leave it there a long time, it gets thicker and thicker layer of dust on it. The longer something sits, the more dust is going to collect on it. Ocean sediments are thinner near the ridges and thicker near the continents and trenches. So you have the same sort of symmetry on either side of the ocean ridge. So again, thinner sediments near the ridges, thicker sediments near the continents and trenches. So they get thicker as you move away from the ridge. So again, this is sort of the whole picture's worth 1,000 words kind of thing. This diagram kind of shows all that other in one spot. So for example, you've got your mid-ocean ridge marked right here. You got younger rocks that are closer to the ridge on this side. You got older rocks that are further away. So it's just kind of showing on this side of it, well, these are younger rocks, these are older rocks. So on this side, you'd have younger rocks here. You have older rocks over here. This is marked with the thinner sediments right here, closer to the ridge, thicker sediments further away. So you can just as easily as said, younger rocks with thinner sediments here, older rocks with thicker sediments on out here. So magnetism. So Earth's magnetic field is generated by the flow of molten iron in the outer core. And again, you have the molten outer core, you have the solid inner core, and the movement of the molten outer core sort of around that solid inner core is kind of what's creating our magnetic field. And this causes compass needles to point to the north, which again, if we have a magnetic reversal, those compass needles will then point to the south. But a magnetic reversal happens when the flow in the outer core changes and Earth's magnetic field changes direction. So instead of a compass needle pointing north, it's suddenly going to start pointing south. So this has happened many times in Earth's history. The current magnetic field is considered what we call normal polarity. Okay, so right now we call it normal polarity. We think north is up. Like on a map, north is up. Compass needles will point north, which in this room is towards the office right there. But the opposite field, we call that reversed polarity. So reverse polarity, a compass needle, instead of pointing towards the office here, would actually point towards that door over there, that yellow door. So that would be reverse polarity. All right, so this is just sort of showing normal versus reverse polarity if we think about the Earth as having a big bar magnet in it. On the left, we've got normal magnetic polarity, or the normal magnetic field. You may wonder why. I mean, you got the south end of a bar magnet right here that's pointing towards the North Pole. Well, if a compass points to the North Pole, okay, so if a compass is pointing to the North Pole, it has to be pointing to a south pole of a magnet. So, because the North Pole of a magnet will point to a south pole of a magnet. So, the pole of the magnet that we call the North Pole because it points to the north, well, it's actually pointing to a south magnetic pole in the northern hemisphere. So there's actually a north magnetic pole in the southern hemisphere. So in a way, it gets a little easier when you start talking about magnetic fields instead of really thinking about them as north and south. We're going to do a lab later, and we'll talk about them as positive and negative instead of thinking about them as north and south, because when you think about the directions, it gets kind of confusing. But if you have a reverse polarity, basically this bar magnet, you kind of think about picking it up and just flipping it over so that the north would be facing in the up direction, south would be facing down. So now your compass is going to basically point in the wrong direction. If you kind of look, you got field lines drawn in here. So we think about magnetic fields as flowing, as moving. So normal magnetic field, they're flowing from the north, or from the south, rather, from the south pole of the Earth to the North Pole. So they're kind of flowing sort of out of the South Pole, up and back around into the North Pole. If that reverses, then they're going to flow in the opposite direction. So they would flow from the magnetic, or they flow from the geographic North Pole to the south, the geographic South Pole. So they're going to flow in the opposite direction. Okay, so magnetic polarity timescale. So paleomagnetism is the study of the history of Earth's magnetic field. How do we do that? We basically look at iron-bearing minerals like magnetite. Go back to our minerals chapter. We talked about different minerals, and magnetite was one of those. It's an iron oxide mineral. But when it crystallizes, as lava cools, basically those magnets, or those little iron crystals, start to line up with Earth's magnetic field. They're like tiny little magnets, and they all kind of line up with Earth's magnetic field. So the minerals behave like tiny compasses. And again, they align with Earth's magnetic field. And that's kind of records what the magnetic field was at the time that rock formed. Was north up or was north down? So data collected from this led to the construction of a magnetic polarity timescale, which is basically what's over here on the right. And this does go back to about 5 million years ago. It's back here. The red, like the red right here, red right there, that is normal polarity. That's kind of where we are now. We're in normal polarity right now. The yellow is reverse polarity. You kind of see some of these, it'll stay one way for quite a while. So actually, here about 1 million years ago, back to almost 1.8 million years ago, 1.7, it was reverse polarity for quite a while. And then we had this little flip here to normal polarity, and then it reversed back to, reverse polarity, and now it's back to normal polarity. It's been normal for a long time. And actually, this is one of the biggest gaps right here that we've had, except for like that reverse polarity back about 1 million years ago. So it's part of the reason they would think, scientists think we're overdue for a flip, because it's been normal polarity for a long time. And the magnetic field's weakening. So
Technically, since that starts at reverse polarity.
So magnetic symmetry, ocean crust is mostly basaltic rock. which contains large amounts of iron-bearing minerals. So that makes it ideal for kind of recording these magnetic changes. So magnetometers are towed behind ships to record the magnetic orientation of the rocks on the ocean floor. So literally this is just put in the water behind the ship sails along and is recording these changes in the magnetic field as it goes along. Regions where normal and reverse polarity formed a series of stripes parallel to the ocean ridges. So the ocean ridge is basically right here. And then you have these stripes. So again, red is normal polarity. So you have these are named different things, but you got the brunes here, which is normal. That's kind of where we are now. The Matayuma, I'm going to do my best to pronounce these. We'll see. That was a reverse polarity, but if you notice, it's on the right side of that ridge. It's also on the left side of that ridge at about the same spot. The Gauss, this would be normal polarity again. And again, it's on the same on each side of the ridge. And then the Gilbert, which was another reverse polarity, which is also on either side of the ridge. And these all run parallel to that ridge. So they're all running the same direction as that ridge. And the stripes match up on either side. So if you got a reverse polarity a certain distance away from the ridge on one side, you got a reverse polarity about the same distance on the other side of the ridge. So the pattern of stripes was the same really on either side of the ridge. And that's symmetry. We talk about symmetry. That's basically what symmetry means. You divide something down the middle and you get a mirror image on either side. So comparing patterns between ocean and land. First off, we got to think about which is easier to look at and study, rocks on the land or rocks in the ocean. And honestly, rocks on land are a lot easier to study and look at because they're not 3 miles underwater. But patterns on the ocean floor were matched to patterns on land. It's possible then to determine the age of the ocean floor from that magnetic recording. So you find a spot on land where you've got the magnetic field recorded. You can kind of match that up with what's on the ocean. You can get the age of the rock on the land, and you can kind of match that up to what's on the ocean floor. So this created what we call isochron maps of the ocean floor. So what is an isochron? Well, an isochron is an imaginary line on a map that shows points that have the same age. Remember, we had this as a word root earlier. This iso. Iso means the same, right? Talk about isobars and meteorological maps that show areas of equal pressure. We had the contour lines, which are sort of an isogram, which is sort of a line that's kind of showing equal elevation, etc. Well, an isochron is an imaginary line that shows points that have the same age, chron referring to age. Young ocean floor crust, again, near the ridges. Older ocean floor crust was found along deep sea trenches. So again, this kind of just goes back to where we figured out. This is kind of how we figured out. It's like, oh, it's younger near the ridges and it's older near the trenches. Okay, so this is the diagram or a map showing the age of the ocean floor, where red is our youngest, up to blue is kind of some of the oldest, purple is the very oldest. Really, the only purple we've got on here is in the Mediterranean Sea here. So this is why we kind of say the oldest ocean floor is like 180 million years, because really that is some of the oldest ocean floor we have. Except for this bit like under the Mediterranean Sea here. So if we kind of look down through here, this is the Mid-Atlantic Ridge. It's red, which basically is saying it's very young. And it basically goes to yellow, which is older, green, which is older, and then all the way down to blue, which is, again, our 180 million years. So the youngest is right here along the ridge, and it gets older and older and older as you get closer to the shore. It does the same thing on the other side. It's younger. It gets older and older and older until you get over here to the African coast. This is the East Pacific Rise, which you can kind of see is a lot wider, but still kind of following the same pattern. It gets younger as you get further away from it. Kind of shows too where this is narrower here. It's expanding slower than the East Pacific rise. This is actually spreading pretty fast here versus compared to the Mid-Atlantic ridge. So seafloor spreading. So seafloor spreading then is the theory that explains how new oceanic crust is formed at ocean ridges, slowly moves away from the ridge, and then is destroyed at deep sea trenches. So it's like a conveyor belt. It forms at the ridge, kind of moves away from the ridge to the trenches, and then gets recycled, and then goes back into the mantle, and then eventually that will come back up and start the process over again. But magma is forced upward along the ocean ridge because it is less dense than the surrounding mantle. Okay, so that magma is forced up through the crack at the mid-ocean ridge, through the rift. As the two sides of the ridge separate, the magma fills in the gap and forms new ocean floor. And then that process continues, producing more new ocean floor, which slowly moves away from the ridge until it gets to the trenches when it's subducted and basically gets molten again or gets melted again, and then continues that process. So, and our diagram over here, yeah, the entire island of Iceland lies on the mid-ocean ridge. Basically because the seafloor is spreading, Iceland is growing larger. In 1783, more than 12 square kilometers of lava erupted, enough to pave the entire U.S. interstate freeway system to a depth of 10 meters. Okay. So kind of put this all in a diagram, trying to visualize it here. So you have the mid-ocean ridge, again, which is right here, sort of in the center. You have magma that basically is coming up under that ridge. The magma basically intrudes, comes up through that ridge, cools, solidifies, crystallizes, forms new oceanic crust. That then moves away from that ridge. Okay. And that's basically where it's being formed at the mid-ocean ridge. And then as this crust, this oceanic crust, moves away from the ridge, eventually it gets to a point where it is subducted, ends up going back into the mantle, where it melts. And then as it melts, it starts to work its way back up to the surface, and that's where we get our volcanic islands. So over on this side, we have islands. So these are volcanic islands that are produced. Or if there is a piece of continental crust that it's being subducted under, you get volcanoes on land. If I can spell that correctly. So you get volcanoes on the land here on this side. Wegener's idea revisited. So while Wegener had a lot of data showing that the continents were once together and they drifted apart, he could not explain how it happened. That's largely why his idea was rejected. He couldn't explain how it happened. There wasn't a mechanism. Seafloor spreading completed his model. It added a mechanism. It gave a process that could cause the continents to separate and move apart. Continents are not pushing through the oceanic crust like Wegener suggested. Instead, they are moving like passengers on the ocean crust as it moves slowly away from the ocean ridges. So instead of them kind of plowing through the ocean floor like he suggested, they're really just kind of riding along on the ocean crust. This led to a new understanding of how Earth's crust and upper mantle moved.